Hello everyone, welcome back to my channel. Today we're diving into the Embedding Gemma Colab notebook, and I'm going to walk you through, step by step, how to generate embeddings, calculate similarities, and even use prompts to get the most out of this model. Before we dig into the notebook, I highly recommend watching my previous video where I explain what Embedding Gemma is and how it becomes incredibly useful when you're building AI applications that require semantic search, fast, accurate, and efficient search capabilities that actually understand meaning, not just keywords. So let's set the stage. Gemma is a super lightweight, open-source embedding model that's perfect for running fast, high-quality AI tasks directly on edge devices, yes, including your phone. It has 308 million parameters, which sounds compact compared to huge LLMs, but this model genuinely packs a punch. You can run advanced techniques like retrieval-augmented generation, smart routing, and semantic ranking without sending data to cloud servers. It works completely offline, making it ideal for privacy, latency, and cost control. Now, the first thing you need to do is access Embedding Gemma on Hugging Face and accept the license. Once that's done, install the required libraries. Gemma follows the sentence transformers architecture, so you'll install sentence transformers and a couple of supporting packages. These work seamlessly across CPU and GPU, and in Colab you can easily toggle the runtime to GPU for a speed boost if you have it available. Next, authenticate with Hugging Face. Log into your account, create an access token, and paste that into your Colab environment. Then import the sentence transformers library. Load the Embedding Gemma checkpoint, and you're ready to generate embeddings in just a few lines. From there, the model spins up on CPU or GPU and starts producing embeddings for any text you provide. Let's answer the big "what is an embedding?" question with confidence. An embedding is a numerical vector representation of text. This can be a word, a sentence, or an entire document. The key idea is that it captures semantic meaning. That means the model maps language into a high-dimensional space where similar meanings appear closer together and different meanings appear farther apart. This is how computers can measure meaning using math. A classic example: apple, banana, and car. If we embed these three words, apple and banana end up closer to each other than apple and car because apples and bananas are both fruits. This is the semantic structure that embeddings learn. It's not just string matching, it's conceptual proximity. When you pass longer sentences or documents, the same principle applies. Semantically similar texts cluster together. Embedding Gemma outputs 768 dimensional vectors by default. That number is the length of the vector for every piece of text. Why does this matter? Because with those 768 numbers, we can compute similarity between any two texts, most commonly using cosine similarity. The higher the cosine similarity, the more semantically related the two texts are. To make this concrete, let's look at three levels of similarity. High similarity: the chef prepared a delicious meal for the guest, versus a tasty dinner was cooked by the chef for the visitor. Same event, same meaning, different wording and grammar, active versus passive. Embeddings pick up that these are essentially equivalent. Medium similarity: she's an expert in machine learning versus he has an interest in artificial intelligence. They're related. AI and ML share a domain, but one is expertise, the other is interest. So they're connected but not identical. Low similarity: the weather in Tokyo is sunny today versus I need to buy groceries this week. Completely different topics, no meaningful overlap, and embeddings will reflect that with a low similarity score. When you run these pairs through the notebook, you'll see the similarity scores align with intuition. The chef pair scores high, the ML/AI pair sits in the middle, and the Tokyo/groceries pair is low. Now, let's talk about prompts and why you might want to add them. Prepending short, task-specific prompts to your text can optimize embeddings for a purpose, like classification, search, or Q&A. Suppose you need to route customer queries to the right team. Consider 2 incoming messages. I can't log into my account. I want pricing information for your enterprise plans. The first belongs in technical support, the second belongs in sales. By adding short role hints, for example, category, support versus category, sales, or by embedding each label, support, billing, sales, technical, alongside the query, the model creates a vector space where queries naturally cluster with the right labels. The embeddings capture those contextual differences and make routing reliable and fast. Another quick scenario: the login screen freezes even after I reset my password. Technical issue: I'd like to inquire about enterprise pricing. Sales inquiry: Using embeddings, you can measure which label vectors are closest to each query vector and assign the ticket accordingly. This makes your support pipeline efficient and your user response time shorter. Pair embeddings with your LLM for answers, and you get professional, even personalized responses with the right context at speed. Let's zoom out and talk about why Gemma is so efficient. With 768 dimensional embeddings, you get rich semantic representations. But what if you need to store millions of vectors or run this on extremely constrained devices? Enter Metatocia Representation Learning, MRL. Think Russian nesting dolls for vectors. The idea is that you can truncate embeddings from 768 to 256 or even 128 dimensions while preserving most of their semantic power. Smaller vectors mean less storage, faster retrieval, and often negligible loss in quality for many use cases. Here's what that looks like in practice. If you compute cosine similarity for apple versus banana and apple versus car at 768 dimensions, you'll see apple, banana, apple, car as expected. Now truncate to 256 dimensions and compare again. The ordering remains the same. Truncate further to 128 dimensions, still the same ordering, and usually very similar scores. That consistency is exactly what you want for scalable systems, reduced resources without losing the semantic ranking. In your notebook, you can repeat this with sentence pairs too. For example, the chef prepared a delicious meal. Pair should remain top-ranked even when you go from 768, 256, 128. Sometimes with very aggressive truncation or certain edge cases, you might notice a drop in absolute scores, e.g., a similarity dipping to around 0.55, but the relative ordering typically stays stable. That's the core promise of MRL, smaller vectors that still behave like their larger parent vectors. This efficiency is one reason Embedding Gemma is so compelling for on-device search, clustering, recommendation, semantic deduplication, and RAG. You get the speed of local inference, the privacy of keeping data on the device, and the cost savings of avoiding cloud calls, plus the robustness of maintaining semantic quality even when vectors are truncated. Let's now walk through the Colab flow at a high level so you can follow along. Set up the environment. Open Colab, switch to GPU if available, and install sentence transformers plus any extras. Authenticate with Hugging Face. Create and paste your token once per session. Load the model. Initialize the sentence transformers model with the Embedding Gemma checkpoint. Encode text. Pass your strings, single words, sentences, documents to get 768 D vectors. Compute similarity. Use cosine similarity to compare pairs or define nearest neighbors. Task prompting. Optional prepend short prompts or embed labels for classification/routing. Truncate, optional if you're implementing MRL-style truncation. Project vectors down to 256 or 128 and validate that your rankings still look good. Evaluate, run your high/medium/low similarity examples and verify the scores match intuition. Now a couple practical tips that make a big difference in real projects. Normalize your vectors, L2 normalize, before computing cosine similarity. This standardizes magnitudes and makes similarity comparisons more consistent. Batch your encoding when embedding many items to fully utilize the GPU and cut down total runtime. Index your vectors with a similarity search library, like FAISS, SCNN, or an approximate nearest neighbor index in your vector DB, when the corpus grows beyond a few thousand items. Store metadata alongside vectors, IDs, titles, tags, so that your retrieval step can return rich, actionable results. Evaluate on your own data. Public examples are great for learning, but the truth is how well embeddings separate the concepts your app cares about. Let's connect this back to the user experience. When your app receives a new query, you embed it and search against your index. Because the embedding space encodes meaning, the results you surface are semantically relevant, even if the user didn't use the exact keywords stored in your content. That's why embeddings feel smart. They are resilient to synonyms, paraphrases, and reordered phrasing. Now, let's return to the prompt-optimized flows with a concrete mini-demo structure you can follow in your notebook. Create label strings like support, billing, and sales. Encode the labels once and cache their vectors. For each incoming query, encode it and compute cosine similarity to each label vector. Route to the label with the highest similarity. Try it with the two queries we discussed. The login screen freezes even after I reset my password, should land in support. I'd like to inquire about enterprise pricing, should land in sales. Extend this to more nuanced labels, account access, refunds, integrations, partnerships, and you'll see the embedding space remains well-structured. If you add short task hints like route, support, before the support examples when you build your label corpus, you can make the separation even sharper. Alright, let's circle back to the apple, banana, car example, and make it actionable. In your notebook, embed those three tokens and print the vector shapes. You should see 768. Then compute pairwise cosine similarities. Sim, apple, banana, high. Sim, apple, car, noticeably lower. Sim, banana, car, also lower. Now apply a simple projection or truncation to simulate MRL. Keep only the first 256 dimensions, recompute similarities, and compare. Then drop further to 128 and compare again. You should observe that while numeric values may shift a bit, the ranking stays consistent. Apple, banana remains closest. That's the Matryoshka-style behavior in action. Smaller dolls nested within the larger embedding still preserve global relationships. One common question: if I truncate too far, will it break? The honest answer: it depends on your domain and task. For many semantic search and routing tasks, 256 or 128 dimensions still perform extremely well. For highly specialized domains or subtle distinctions, you might prefer to keep the full 768 dimensions. The right choice balances quality, latency, and storage for your deployment target. Let's also address what embeddings do not do. You can't decode an embedding back into the exact original sentence. The mapping is one-way and lossy on purpose. If you want to get text back, you use embeddings to find the nearest text in your index corpus. That's how search recommendations and RAG pipelines use them. Embed, retrieve nearest neighbors, feed those into your LLM. A quick note on deployment scale. Because Embedding Gemma is compact and runs offline, you can build experiences that feel instantaneous. On-device semantic search for notes, messages, or documents. Classification and routing on mobile without network calls. Deduplication and clustering for local content libraries. Personalized re-ranking of results where privacy matters. If your corpus is large, say hundreds of thousands or millions of items, pair Gemma with an ANN index for millisecond-level retrieval. Use vector normalization, quantization if needed, and memory-efficient stores to keep everything snappy. If you're building a full RAG pipeline, embeddings become your front door to the knowledge base, ensuring your LLM gets the right passages, not just any passages. Let's quickly recap the similarity tiers with the exact examples we ran earlier. High similarity. The chef prepared a delicious meal for the guest versus a tasty dinner was cooked by the chef for the visitor. Same event, different phrasing, scores high. Medium similarity. She's an expert in machine learning versus he has an interest in artificial intelligence. Related domains, different levels of involvement, scores in the middle. Low similarity. The weather in Tokyo is sunny today versus I need to buy groceries this week. No semantic overlap, scores low. When you run them in Colab, you'll see those scores come out exactly as expected. If you try a truncation pass, 768 to 256 to 128, the ordering remains the same, which is the behavior you want. To close the loop on setup, after you've accepted the model license on Hugging Face, installed sentence transformers, authenticated your token, and loaded the Gemma checkpoint, you can run through your cells. Generate embeddings for test words and sentences. Compute pairwise cosine similarities. Add small prompts or embed label strings for routing. Truncate to smaller dimensions, remeasure, and compare. Optional. Create a tiny app cell that takes a user query, returns top K nearest sentences from a small corpus, and displays similarity scores so you can see the semantics working live. You'll notice that even as you reduce dimensions, your apple versus banana relationship remains strong, while apple versus car stays clearly separated. If you see a score like 0.55 at a lower dimension and it worries you, focus on ranking and thresholds. You can calibrate a threshold for match versus no match and still get reliable behavior. What matters most is that relevant items rank higher than irrelevant ones. Finally, let's connect this to your broader AI workflow. Embedding Gemma is an ideal front-end semantic layer. It transforms your raw text into a format that your search, classification, and RAG systems can reason about instantly. Because it's lightweight, fast, and offline friendly, you can ship real-time, privacy-preserving experiences to users without sacrificing quality. Combine that with Matryoshka-style truncation, and you can scale to huge corpora or tiny devices without losing the semantic essence. So, that's our plan for today's session. We covered what embeddings are, and why semantic similarity matters. We set up the Colab notebook with hugging face-off and sentence transformers. We generated 768 dimensional embeddings and measure high, medium, and low similarity cases. We use prompts and label embeddings to route queries to the right teams, support versus sales. We applied Metatocia Representation Learning ideas by truncating vectors to 256 and 128 dimensions while preserving rank order. And we discussed how to deploy this efficiently inside your apps and pipelines. I'll include links to the research and the code samples in the description so you can experiment directly. If you missed the fundamentals, definitely watch the previous video first. It gives you the conceptual base that makes today's notebook walkthrough click. Now let's jump into the Colab cells and start building with Embedding Gemma.